Alrighty, welcome. In this module, we are moving on to chapter 10, and we will continue our discussion of hypothesis testing and really build upon this framework of how we approach any assumption we make and how we can actually start to test it using this hypothesis testing framework. So in last class, we talked about testing the means, and this class will dive a little deeper into testing means between different populations, and then also build upon that with the chi-square distribution and starting to test variance, which will get us towards the culmination of this class when we start to get into ANOVA testing, which is analysis of variation. So a lot of these fundamentals will continue to build on each other and will be very similar with how we approach the same framework of hypothesis testing, but we'll be using different distributions, and depending on the problem that we're solving, test it a little differently. But a lot of this will be similar to last class. We're just going to build upon the framework and add new tests to our arsenal. So if you recall, when we even started getting into this, when we talked about the t-distribution and we had William Gossett trying to create the best beer that he could, and the way he was testing this was using different samples and seeing if changing something like the soil fertilizer might yield better crops. And the way he would actually test this assumption of if fertilizer is added, will the quality of hops be better in this group than the other group? He applied this type of framework to test if the means of the quality, again, we were thinking about like height as just as an example, if the means were statistically significantly different between the two groups, then we could say with a degree of certainty, hey, these two groups are statistically different, therefore adding fertilizer to one sample boosts the yield quality. So in this chapter, we're going to be talking about this exactly as we start to compare the means between two populations. And we'll follow a very similar procedure for estimation and approach for setting up our tests. So just another example of how this might relate to real life. If you were trying to assess the differences between the average bike ride time for city bike usage in New York City, let's say you wanted to know, is there a difference in the average time spent riding the share bike between male and female patrons? We can use this testing framework to see if the average time on a bike share is larger for the population of women. And this might us help understand, is there any difference between the population groups? And in order to make any inferences between two populations, we must assume that the samples are independent and identically distributed random variables. And this essentially just means that the samples are completely unrelated to one another. When we collect data from one population, there just can't be any overlap between the data from the second or third population. And really the rationale behind this is we don't want to be capturing underlying influence between groups. So this is just an assumption we make. And this just is defining that the samples that we are going to be testing are clearly delineated from each other. And part of this as well is this normal distribution, again, that is assumed in order for us to use the symmetrical nature and these tails to use our same Z table and testing the area under the curve. And why is this useful? Why does this matter? This is useful for us to be able to test that two samples are derived from two independent populations. And next class, we'll get more into testing if things are independent, if testing that they are normally distributed. So this is really just getting us to the point where if the means between two samples, if we subtracted one from the other and got to 0, because that would essentially mean that the means are the same. If you subtract one from the other and you get to 0, that would say that the means are the same. And if we see a value greater than 0, we can assume that the means are different. And then we'll use our testing framework to establish how different do the means need to be in order for us to test that these two samples are derived from two independent populations. So I bring up this type of framing of the question because really we're just trying to test that these two samples are from two different populations. So getting back to our example of city bike users, if we don't see any statistically significant difference between, let's say, a male and female group, we would see these distributions essentially clustered together, where we wouldn't actually be able to see these differences in the group populations, because it would be male and female have no difference in the average ridership time, and therefore you wouldn't actually be able to use statistics to even be able to differentiate between a male or female rider. But if there was a difference in the average ride time, we would see these distributions start to emerge. And that's why I find it helpful for our class to be able to plot histograms on the same axes, because we would use this type of approach to really test, are the distributions different? Any questions so far? Because this really establishes the foundation for what we'll eventually be testing. All right, seeing that there's no questions, we'll get into some of the more technical aspects, because again, we just kind of need these tools to be able to run through our framework. And this slide just defines a lot of the different inputs that we would need to have for testing our understanding of the world. So this would be how we would calculate this confidence interval. And this is the same approach we would take last time. If you have that margin, the confidence interval, we use alpha to measure to what degree do we need to be certain enough in order to reject or accept the null hypothesis. So none of that in 101 minus alpha % confidence interval should be new. That'll be the same. And really what this first line says here is talking about how we would test that confidence interval, where we would have that difference between the averages between group 1 and group 2, plus or minus this population variance between the two groups. So we use the same type of aspect that we really started when we talked about confidence intervals, and using it here as well, where in line 2, this would be used when the variance is considered unknown. That's when we would use the t distribution. When the variance is known, we can use the z distribution, or the z-test and the t-test. So that's really the main difference between 1 and 2. And this is when we don't know the variance, but we can assume that they're equal, which is just an assumption that allows us to really use this formula. And if we need to use 3, that is when the variance is considered unknown and cannot be assumed equal. And this gets back to the question, even Darren, you were asking about, of when do we need to use the degrees of freedom? And we would be able to use this pretty much based off of the data we have available. If we actually know the population variance, we can use the first one, and the other two formulas based off of what information we have available. So this is pretty similar to our chapter about confidence intervals, and we use the point estimate plus or minus this margin of error. And now we're using our z distribution or the t distribution to calculate the necessary inputs to then test our assumption. So next we'll go through an example of how we work through this, but any questions on the slide now?
Yes. So the variance, is that just basically the population or the sample population?
What do you mean by the question?
So you said for the first one, we use the z-score because we know the population variance. And for the second one, the second formula, we use a t-score because we don't know.
Exactly.
Now the population variance is like the number, like the sample size, or is it something else? Because I just want to make sure I know what it is before we go on.
Yeah, that's good to talk through, because the population variance is as if we had an understanding of the population that we're trying to estimate from, and we know the variance of that population. So most of the time in real life, you don't actually really know the population variance, but you might have a sample size that's large enough so that you can assume that your sample variance is representative enough of the population variance. And so that's why most of the time you can use number one, but when your sample size is too small, usually, under 30 is kind of just this accepted value. We don't necessarily, and we don't have that sample variance to use in this case of the population. Like, we don't know enough about the population variance to actually use the sample variance. That's when we would use the 2 and the 3 formula. So the variance is specifically, similar to standard deviation or the mean. This is how we calculate the dispersion of a variable. And this is more so just making that distinction of when we do have enough samples in our observations to say this is the population variance. Most of the time in the textbook, it's essentially just given to you, like this is the population variance. But when you have too small of a sample and you might not necessarily have this understanding of what the population variance would be, then you would use the t-distribution because we're using the sample variance instead.
Got it.
Great question, though.
I try.
All right. Any other thoughts before we move forward? Okay, so let's go through an example where this would be, it's similar to last time. We have one-tailed, two tails, where that's essentially depends on the question that we're asking. If we're looking to something greater than or less than, or if these two things are just equal to each other, that's how we would determine whether we're talking about a one or two-tailed test. So we take the same exact steps as we applied in this null hypothesis significance testing framework, sometimes also referred to as NHST, where we would first just identify what's the relevant population parameter of interest that we're trying to test here. And in this chapter, we'll be talking about like the means still. So in this case, we are trying to talk about something for diversity between different companies. So this is just a hypothetical question. You are trying to see if there is a difference between the average director diversity. Let's say this is just a proportion of members on your executive team and C-suite that are considered diverse. So let's just say that this is a definition of a term of director diversity score or something like that. And we want to test, does the average diversity in the director score statistically differ between companies that are listed on the NASDAQ or the S&P 500? So this is just an example that I came up with because it might be interesting if you wanted to test, are there any correlations between companies that have more diversity and their return on investment. So something like this relates to environmental social governance. And we could use this type of framework to actually test, is there a statistically significant difference between the diversity between companies listed on these two different indexes? So we want to test the means between these different groups. So therefore, this would be the null hypothesis, which would, again, this is testing the default, or back from last class, this is essentially, this is you're innocent until proven guilty, and we need to collect more evidence to find reason for guilt. So in this case, our null hypothesis is saying that there is no difference in director diversity between the NASDAQ companies and the S&P 500. So we need to collect evidence, take a sample from these different populations. And if the mean is different enough between these, we are finding evidence to reject the null hypothesis and use this alternative hypothesis to say that the means are different enough, but different enough depends again on our significance level that we establish in the beginning, or that value of alpha. So like how far away from the expected value do we need to be in order to say this is statistically significant enough, and not just, kind of random chance or the general variance that might exist. But we need to know that they're different enough to say that the S&P 500 has more diversity in their director and C-suite compared to the NASDAQ. Let's just go through another example where this would be,
sorry.
No
So
worries.
would this one be a two tail? Or is it one tail? Because they're equal, right?
This is the two tail because we are trying to just see if it's how far away from zero is it? Is it 2 standard deviations away from zero to say that it's different enough?
Because it's equal to 0. That's why. If it was greater than or less than, it'd be one tail.
Exactly.
Got it. Just wanted to make sure.
Yes, exactly. And it's good just to think through it too, of like, what is it that we're testing? And yeah, you can kind of use that rule in your mind. If it's, less than or greater than a value, we're talking about a one-tailed test. And when it's equal or not equal to 0, we're talking about a two-tailed test. Which kind of just prompts us for this next slide. It's a good lead up into how we would frame this one.
A one-tailed test.
Pardon?
A one-tailed test.
Yes, exactly.
There
so
we go.
What do you think this would look like for our null hypothesis?
So is greater than it'd probably be H or H1. I'm sorry, H1 or HA, whatever it is called, or the mean 1 greater than mean 2, or mean 0 greater than mean 1, whatever they're called. I forgot.
So for the null hypothesis,
It'd be, oh, my bad. Mean 1 minus mean 2 is greater than 0, or greater than whatever the thing is. Oh, well, somewhat.
But it's exactly what you're saying. Like, we're subtracting the means, and if it's less than 0, then we're saying that the mean of whichever we want to associate with 1 or mean 2. So in this case, NASDAQ, it could be mean 1, and S&P 500 is mean 2. But pretty much what you were saying is what we would use for this as well. So yeah, we would subtract them from each other. And if this value is less than 0, we could say that, we can't say that the average director diversity is greater for companies listed in NASDAQ compared to the S&P 500. But if it is, then we have evidence that we should reject this null hypothesis to say it's greater than. And if we wanted to do this the other way around, this would still be that one-tailed test. And by other way around, if we wanted to say, it's less for NASDAQ than it is the S&P 500, we would just need to change these different, Boolean statements. And these are the test statistics we would use. So similar to previous chapter, how we would use it is the same. The only thing that's really changing are the values we would use for these different formulas, where now we're testing the difference between 2 population means. And again, similar to when we were talking about the confidence intervals, this is the same breakdown of 1, 2, 3. So 1 would be when we do know the variance of the population. So in that last example, we could use this first formula because we can know the population of the S&P 500 and the NASDAQ. because it's more finite, and we could know this variance of the population. So in example 2, that would be when we need to use the t distribution, because we don't know the variance of the population. So we would use a sample variance instead. And we would use this formula. But again, this is getting more into the nuances of when you apply this in real life, kind of knowing what is the sample you're using from, and is the variance, can it be assumed equal? We would need to essentially do more testing in real life to be able to choose between 2 or 3. But most times in the textbook, it'll essentially just tell you what you need to use for the inputs. But thinking about this, when the variances are unknown, can we assume them equal? We would use this as 2. And if we can't even assume that they are equal, then we would use 3 for the different formulas. But you can see they're relatively similar in how it's computed. We just have different values where we would need to multiply by the sample variance in 2, whereas in 3, we don't have that, but we use this aspect of degrees of freedom. So I think it's interesting just to see, depending on the information we have available, how do the formulas change? But for the intents and purposes of our class, it'll usually tell you what you'll need to use for the homework, at least.
Thank God.
Well, yeah, so most of the times you can kind of start from 1, and if the sample isn't large enough, you might have more reason to use 2 or 3. But again, if this was in real world, you would probably need to just do more research to know, can you assume the variances are equal or not? But let's get into an example from the demo where these are the different testing frameworks. So depending on the question, are we testing the means being equal, or are they less than or greater than? So this also kind of just gets into the impetus for me asking that hypothetical of, trying to compare if different proportions of male to female, for example, have any types of differences. So I think it's interesting to think about, and it's very relevant to the real world. All right, so let's go to the demo, where we will just run through this first part of the module, where we will just be testing the means of 2 different groups. Okay, and so just as an FYI, since we have more folks here joining us today, which is awesome, I really encourage it and appreciate your time to join us in class today. But this meeting will end in 10 minutes, so we'll just need to restart again wherever we leave off. So maybe that'll get us right through this demo, and we'll have a nice clean transition. Okay, so this example will be working with expenditure and default data, where we'll have this credit card data, which I believe is what we used last time as well. But rather than testing, the age of who's likely to not get approved, now we're going to test the differences between, folks who have the approval equal yes, and those who have the approval equal to no. And we'll just start to test if there is a difference in the average income for credit card applicants that are accepted. Kind of just naively, you might assume as this analyst saying that folks who get accepted for a credit card, it must be because they have a higher average income compared to folks who do not get accepted. So this would be our claim, where we would specify the different hypotheses and state a significance level. Again, it's important you state the significance level before you get testing. Because otherwise, depending on your test results, if then you define a significance level, you're kind of working your way backwards in a way that's kind of not ethical to how you should approach this type of question. So we should always define the significance level before we dive in. Otherwise, you might change that significance level depending on what you see, which you should not do. So let's read this in. So it's the same data set as last time, where last time we were exploring if age had a difference for folks who get rejected. And this time we're now going to create a new subset for people who get approved and people who get rejected based off of this column of card, which dictates the outcome. So I'm just going to see what are the value counts, just so we kind of know the relative proportion in our sample size. It's always good to just generally explore the data a little bit more before you dive in. So seeing this, we know that most of the folks in this sample did get approved, but we have this subset that did not. So when we create these subsets, we are taking this full data frame and creating two new subsets that just have when it's approved and when it's rejected. So that's when I print out these different shapes, we see the subsets align with the value counts. And our relevant parameter is the mean income between the two groups, since we're trying to test if the average income is different. But this case, we're not just saying that they're different. This analyst's claim is that for the group, and I'm just going to refer to them almost as like populations, just so we can keep consistent in what we're actually testing here. We're trying to test if the population for people who were accepted, if their average income is greater than the population of folks who get rejected. So that's why we use this one-tailed, because we want to see if the value of mean 1 is statistically greater than mean 2, to say that it is bigger for people who get accepted. And I'm just going to set this confidence interval at this threshold of alpha to say we need to have it be 99%, kind of where if we were to test this 100 times, 99 out of 100 would give us this type of expected. Well, actually, we should rephrase that a little bit. That's essentially saying only 1% of the time would this kind of just be due to random chance that we would see a value at least as extreme as what we might see here. But we'll revisit that as we start to test this for how we should really interpret this. But in its core, we're saying, is the value we see extreme enough that it's not just due to random chance? And if it is just due to random chance, how probable is it that it's just due to random chance? Getting back into how we have those type 1 and type 2 errors. So we set our value of alpha to be 0.01. And I'm going to create the mean and standard deviation for the two different groups. So using that subset we had above, we have the mean and standard deviation of income. And now let's test for, or not test, but create it for the population that was rejected. And we can start to see, just using your eyes, you see it's a little bit lower, but is this low enough to state that there's a statistically significant difference? And is that difference, again, significant enough that it passes our threshold? Okay, so we are using this test statistic. And I'm using this one mostly because, this is kind of more in real life type of example, and this would follow the formula that we had here. I'm just checking my work with which one that we used here, because this takes the means in the top and then takes the square root of the standard deviation of 1, square it to get the variance, divided by the number of observations with the second one as well. So let me just go back here, where that is this first formula here. So I think I need to check this, because we are using this as if it's the population. So it actually is known. But again, we're kind of oversimplifying that this is the population in this scenario. So we're going to use this test statistic, which is just based off of the formula that the textbook says. And it's really just testing the differences in the means divided by the differences in the variation in the variance. So perhaps instead of squaring it here, we could have used the variance as an input, but we use the standard deviation just so we can use the formula exactly pretty much just from the textbook. And so the number of observations, instead of me using that shape value, I'm just using the length of this subset compared to the length of the other subset as our value of n. So let's have our z-score of 3.54, and we convert this into a p-value. And now we can run this through. And so we're pretty much testing, is our p-value, if it's greater than our alpha value of 0.01, that means we don't have enough evidence to say it's statistically significant different. So we would fail to reject the null hypothesis. But if our value of p-value is greater than or equal to our value of alpha, we have enough, this is evidence against the null hypothesis. So we check and I think this is incorrect. It should actually be oh yeah, no, this is correct. Good. I just have to reread it. I've just been checking over my stuff. So we have enough evidence to reject the null hypothesis because the p-value is less than our chosen alpha here. So at this 1% significance level, the average income for applicants that are accepted is greater than, let me just add p there, that are applicants that are rejected. And so the meeting is going to end now. So I think that's a good spot for us to restart, and we will get into how we test different variances. So I will stop sharing now and end the recording, and we will rejoin shortly. Maybe take a quick break, prepare any questions, and then we'll revisit.
Does collab have spell check? Because I've been spelling things wrong for so long.
It'd be great to look into it. I'm sure someone maybe has made some type of package for it, hopefully, but also it's not really